Good morning. My name is Pedro, and I hope to present to you how to use scenario analysis to extract rules with a tool called SIRUS to explore resilient reef futures. This work was done with the help of Takuya Iwanaga. We both work at the decision support team at AIMS. And before I start talking about scenario discovery, I need to talk about what is a scenario. So the scenarios to us are future states of the world. But because we don't know what is a future, we are talking here about a model. So the future is the future predicted by a model. That depends on a few factors. So those factors can represent something we cannot directly change, like environmental factors. But they can also represent something related to a decision or intervention, like how many interventions, when do we start, the frequency, etc. And we can run this model many times, simulating different interventions, also different environmental possible futures. And this way we can generate many scenarios. But the question is, how can we use this model to make better decisions for the future if there's this great range of possible different futures that the scenario predicts? And to this, we are going to use time series clustering together with SIRUS, which I'm going to present next. So the first question is, how can we compare different scenarios? One way would be to use the output of the scenario at some point in time and group together the ones that have the same value. But this is not very trustable because this choice of points in time, so 20 years from now or 10 years from now or 100, is arbitrary, and the scenarios can change a lot, the behavior during time. So depending on this choice, you have different groupings. This is not very trustable. Another way would be to use some metric based on the scenario, like the average value. But again, this is not very trustable because you can have, for example, two scenarios that behave very differently and have the same average value. So you will group them together, but they actually are not alike. And that's why we can use time series clustering. So on the left-hand side, you can see many scenarios generated by a model. And on the right side, the result of applying this time series clustering algorithm, which groups together scenarios based on their time behavior. So for example, here you can see a group of scenarios that have a big drop at the beginning and they are steady, or the ones that have higher values than the others overall, or the ones that are wavier than the others. So this way we can choose one of these groups, for example, the ones that behave better than the others, to target and investigate what is happening there. Just a quick overview of why can we do that, how can we do that. There's something called complexity that captures the behavior of the scenario. So this complexity, I don't know if you can see, but it's just the sum of the variation of the scenario over time. So you can see that if the scenario changes a lot, this complexity will be bigger. And then when you divide one by the other, you have a quotient that is the comparison between the behavior of both scenarios. If this number is close to 1, that means that both scenarios kind of behave similarly. Otherwise, if this number is bigger than 1, it means that one of them oscillates much more than the other. And that's how we can compare two scenarios and take into account this time behavior. And this is the result using ADRIA, which is a software we developed at AIMS. This is just demonstration data, not real data, but just to show an example of how that works. So this is 4,000 scenarios generated by our model. And on the right side, 6 groups created based on those scenarios, changing again the possible intervention factors or environmental factors, biological factors, etc. So this is the big picture so far. We have a model, we can generate many scenarios, and we can group those scenarios by behavior. Now the next step is to interpret. How do we make sense of this? And to explain that, I'm going to use an analogy with the Titanic data set. So this is a data set containing information about more than 500 people on board of Titanic. We have information about their gender, age, type of ticket they had, etc., and if they survived or not. And the question here is not to predict if they survive or not, because we have a lot of prediction models out there. The question here is which information is more relevant to determine the survival rate. So we are interested in knowing if let's say you have a person and I know this person is male, is this information relevant as a predictor of the survival chance? Or maybe knowing the age of a person is a more relevant information as a predictor. So that's what we want to know, not a prediction model, but which characteristic is more relevant as a prediction. And we use SIRUS for that. This is why we use this algorithm called SIRUS. This is an example of what SIRUS does. It creates those trees, those decision trees, randomly. So each time it selects 2 characteristics from the list that we have and a small group of people, and it builds thousands of trees like this one. They will be slightly different. And for each tree, we can extract a rule that is highlighted in this yellow box here. This rule, for example, if a person has a first or second class ticket and is female, then the survival probability is 95%. This rule contains the same information in this tree, so this rule was extracted from the tree. And by creating thousands of trees like this one and extracting thousands of rules, SIRUS can find the rules that appear the most, that are more relevant. So this way we can make sense of this data. On the right side, just a scatter plot with, again, the same information. So the gray area is the one selected by this rule. Each dot is a person. The blue ones are the survivals, and the red ones are the non-survivals. So just another way of looking at the same information. And going back to our example, now instead of trying to predict if someone is going to survive or not, we are trying to predict if a scenario is going to be in the target group or not. So from our 6 groups that we created based on their behavior, we can target one of them and try to see which factors are more relevant as a predictor of a scenario being part of the target group or not. So just an example of a rule extracted by SIRUS. In this case, it is saying that, again, highlighted in the yellow box, if factor A is greater than 2.3 and factor B is greater than 21, the probability of the scenario being in the target group, in other words, behaving like this target group, is 80%. This is relevant because, again, factor A and factor B could be related to some intervention, like how many deployments of something we do, or with which frequency, or when do we start. So we know that from all the things we can change about that policy or intervention, those 2 factors are very relevant to determine if we do that thing that way, the system is going to behave, or the future is going to look like the scenarios inside this blue area in the target group. Yeah, so this is the big picture. One thing we can do with that is do it again. So we can do this same thing in cycles, running more times the model, generating many scenarios, simulating other possible policies and interventions and ecological factors, etc. But most importantly, we can use that to inform discussions and policy and management decisions. That's all. Thank you for listening.
Thank you, Pedro. We have time for open it to the floor. Thank you, Scott. Wait, Rail's bringing you there.
So the clusterings you were looking at were, I think you were saying, were driven partly by the different interventions. But do you get clusterings that are more to do with the sort of stochastic environmental forcing? So if you have a scenario, say, that happens to have just stochastically lots of cyclones over a period, it might cluster differently to another set of scenarios that just stochastically didn't have too many cyclones.
Yeah, so every time we run a scenario, so when I say we have many scenarios, for each scenario we are changing environmental factors. So we have, in this case, the possibility of changing stochastically the cyclones, degree heating weeks, other environmental factors, also biological factors, because there's an uncertainty related to that. So each scenario, we are varying all those things. So when we cluster, the cluster contains both environmental and biological and decision-related factors, everything together. Yeah.
Thanks, Pedro. 2 questions. First is on the time series clustering. There are systems that bifurcate. There are like multiple steady states. And I wonder how your classification will perform, given that those like bifurcating system, they're really like the signal of a single like driver. The second is on your SIRUS. Is that like a statistical analysis, and is it related to a boosted regression that's used usually in ecology?
Sorry, what analysis?
Boosted regression, the SIRUS. I wonder if it's a new statistical analysis or it uses like boosted regression as a...
Okay, I'm going to answer the second one first. So SIRUS uses random forest, sorry. So that's the idea. It's basically a random forest algorithm. It's the basic idea. You build many trees. The difference is before building the forest, it uses as split points the same split points. So for every tree it builds, the possible split points are always the same because they are the n quantiles. So let's say you want 7 fixed split points. So you have the 10, 30, 50, 70 quantiles. But other than that, it's basically a random forest. And about the first question, what I think will happen is that, because when you say a system bifurcates, to me it will be like a few scenarios will go one way and a few will go the other way. And in this case, it will select 2 different clusters for this. Yeah.
Can you explain, Pedro, what's the advantage of having the predefined split points rather than just letting them emerge?
Oh, yeah, of course. This is why the algorithm is called SIRUS, and this S in the beginning is for stable. So if we just use a random forest algorithm, every time we add more points, so let's say in the Titanic case, if we found out 10 more people aboard the Titanic that we forgot, and we add those people in the data set, the rules extracted by the random forest will be slightly different. With SIRUS, when we fix these split points using the quantiles, if we have new data or something like that, or if you just run the same algorithm multiple times, the split points will tend to be the same. This is the stability. So it's stable under new data entering the data set.
Sorry, in the interest of time, we need to move fast.